Okay, let's get started. So, if you haven't picked up your midterm one, today is the last day to do so. So the remaining midterms are up there. If you gave me a regrade yesterday, I have it regraded and it's up here. As well as homework ones. If you haven't picked them up yet, you probably should do so. Okay, any questions from yesterday? No questions? Okay, so what did we talk about yesterday? Or at least start, for the very least. Yeah, right, yeah. So we were talking about trying to generalize the pumping lemma for regular languages to CFLs. And what did we look for repeating something? So for DFAs, we had the repeating state business. So did we look at PDAs then? For looking for a repeated state for a PDA? It was only yesterday. Yeah, yesterday was rough. Well, what did we look at? Did we look at PDAs? Well, we tried to look at PDAs, but what was the issue? Or what made it difficult? Well, if I have a state right here, and I do a bunch of transitions come back, the stat contents might not be the same. So what could happen is, I could take one transition the first time around, and then take a completely different transition the second time around. So the behavior will depend based on what you actually did before in some sense, because the stack will possibly be different. So we saw, okay, PDAs are probably going to be difficult to do this kind of analysis. So we turned to instead what? What was there? Parse trees of what is the object? Yeah, CFG. But parse trees is what we looked at. And we looked at grammars in the general sense, or did we look at a specific form of grammars? Yeah, in CNF, in Chomsky normal form. And why did we look at them in CNF in particular?
Because the number of states we wanted to be 2, so we could have...
Oh, well, yeah, so that could help us in that we now know the structure of the parse tree. It's a binary tree. Whereas in general, we don't really know anything because it could have any number of variables on the right side, not just 2. So CNF was the way to go. Then we looked for a repeated variable from top to bottom. So our picture before, let's make a actual parse tree. So we had this long path from the top to the bottom in this parse tree. After we've taken off the leaves, which are just the terminals of the parse tree. So when we took the terminals off the bottom, the leaves, the only thing that's left are the variables. So this tree just has a bunch of variables in it. Well, if we made this tree tall enough, then there is some way to go from the top to the bottom with a repeated variable somewhere, because the tree is tall enough. So if there's some repeated occurrence of some variable A right here, which cannot be the start variable because of the way CNF works, then we noted that we looked at these 5 pieces right here. And we derive various properties of that. So let's actually state the pumping lemma here. So I'm just going to shorthand it here. Okay, so let L be a CFL. Then there exists, as you might expect, a pumping constant P for L, just like before, such that for all strings in the language with the length of W at least P, and then we'll get to stuff in a second. So the condition let's actually understand why we have these two conditions. So for the DFA case, when we did regular, we required that it was in the language because we wanted to end in the final state. So it had to be in the language for that reason. And we required that the string be length at least p because we guarantee that at some point a state is repeated. But we don't have states here and we don't have final states here. Obviously, no final states here. So why do we have these two conditions here? Why is the string needed to be in the language? Consider if it wasn't. Can I make a parse tree for the grammar if a string is not in the language of the grammar? No, it's not possible. So that's why we have W's in the language, because we can make a parse tree for it. And because we're talking about parse trees, we better have the string in the language. Why do we need W to be at least a certain number in size? What does that guarantee for us? There's a repetition of what, though? Look at the parse tree. What's the repetition we're looking for? The variable. Well, I told you that this parse tree, we took away all of the terminals. But the string we're looking at here, W, is full of terminals. So why is that related to the parse tree? Well, consider the parse tree, but I put the terminals back on. Well, could it be that I just make the string longer and longer and longer and longer, and the tree keeps getting bigger, obviously, and there's no repetition, no matter how big I make the string? Well, consider a completely full binary tree. Well, and let's just say that the height of the tree is p. It's exactly p. Well, if I make the string one character longer than what it requires to be a full binary tree, doesn't that require that the tree become one level deeper? Yeah. And so then we have the height of the tree being p plus 1. So the p here, all that it is to guarantee some number that the tree eventually must become tall enough to guarantee this repetition. Okay? So it's just guaranteeing at some point the height is big enough so that we have this repetition. Okay. So that's why we have those two conditions. Always remember why we have these here, not just trying to remember it verbatim. There's a reason for all of this, I swear. Okay, so all strings in the language with length at least p, such that, so we're going to be looking at one decomposition or all decompositions, not a contradiction proof, just the pumping lemma itself. Do we need only one decomposition to work or all of them? We're not proving by contradiction here. Well, could it be possible? Well, here's a decomposition right here. Could it be possible a different one works if I just picked a different set of rules to do? It could certainly be possible. So we only require that there's one decomposition such that we can pump as much as we want. But when we try to prove something is not regular or not context-free, we want to show every decomposition does not work. Because if I leave one out, that could be the one that pumps and works. Okay? So we only require that there exists a decomposition of W into UVXYZ. So remember, it exists here because if there exists one, then I can pump it as much as I want. But if I want to show that a language isn't context-free, then I got to show no decomposition works at all. Because if one works, then I can pump it as much as I want. Okay, does that make sense? Okay, into those 5 parts, such that, I guess for the third time, such that, we have the 3 properties that we talked about last time. And what were those 3 properties? So what are the parts that we're putting more of into the string over and over? V and Y. So V and Y are the things that we're putting more of in the string. Can I put a different number of V's and Y's, or does it have to be the same every time? The same number. Why is that true? Well, consider copying down the top parse tree down to where the second occurrence of A is. Well, we're going to get an additional copy of V and Y every time. So no matter what happens, I'm going to put in one copy of V and another copy of Y. So the number of V's and Y's is the same. And what we figured out was, if I put I of each of them, then it's in the language for all I at least 0. Why is it in the language for all I? Well, remember for regular, it was in the language because we can go around the loopy part in the DFA as much as we want and then eventually go to the final state, which means it's in the language. Why is it in the language here? Well, if I do this copy-pasty business, then if I take the top parse tree and then copy it down, do I have another parse tree? Yeah, it's a different parse tree, obviously, but I still have a parse tree. So because it's a parse tree, then it's in the language for that reason. Okay? So that's why it's in the language here. What were the other two properties that we derived? What about the V and Y parts themselves? Could one of them be empty? Because I remember the regular one had the part couldn't be empty. Could V or Y be empty? Yeah. Okay. Could both of them be empty? No. Why is that true? If you remember, if the second occurrence of that repeated variable occurs right after the first one, well, if we're looking at the single path through, the other side must generate something, because no variable can make the empty string other than the start variable. So the other side might coincide with the first occurrence and have one of V and Y being empty, but the other side of that sub-parse tree, so if we look at this occurrence of A, and if the second occurrence of A appears right after it, the other side must generate something of the string, because it's not the start variable. So what we require then is that V and Y, the length together is at least 1. And so in other words, i.e., V, Y together is not the empty string. It's the same thing. Okay, and what was the third condition?
I just have a question about this.
Mm-hmm.
So how is it possible to have one as empty and the second is not, even though we're getting the same amount of time?
We're putting the same number of the strings, but the strings themselves can be different. So let me think of an analogy. So think of like you're trying to host a party and you want to order pizza, but this is a different class now. If you're trying to order pizza and some people prefer veggie versus cheese or meat lovers or something, but you realize that the restaurant for whatever reason ran out of veggie pizza, so you order the pizza and then you try to add more pizza to try to make those people happy if possible. So you're putting more copies of the cheese pizza in, but you're still putting the same number of veggies in there. There's still 0. Okay, so because even though there's a different number, you're doing the same operation. Isn't that like the worst analogy possible? Yep. But yeah, so V and Y, they could be different strings, but I'm putting the same number of them in there. So for example, if V is the empty string, if I put I copies of it in there, it's still the empty string, but I'm still doing that operation. Other questions? Okay, what was the third condition? Well, if I remember correctly, the regular version of this had the two first pieces having length at most p. And the reason for that was, if we look at the first repetition, it couldn't occur too far along. Well, what about here? What is the part that's being like repeated if I copy it down? Vxy. So the thing that we derived last time was that Vxy, the whole thing, is of length at most p. Because that's the repeaty part. Something else that's repeating. Okay. Well, here's something interesting other than that. Remember the regular language version. If you remember the x and y part of the string having length at most p, where was the x and y part in the string? Was it like in the middle, at the end, or at the beginning? At the beginning, because the decomposition was x, y, z, and the x, y part has length at most p. So because x, y is the prefix of the string at the very beginning. What about here? What is the prefix, the beginning of the string? Okay, someone's really got it. Anyway, what's the beginning of the string here? What's the very first one of the 5 pieces? U. Is that the three middle pieces that have length at most p? No. So think about what's happening here. The part that we are trying to look at and do some work on, that is not necessarily at the front of the string. It could be near the end, in the middle, or at the beginning. So you can actually see now that the CFL version is going to have possibly many more cases, because it's not necessarily at the beginning anymore. It could be anywhere in the string. So as we're doing these proofs, we're not going to actually do it in a formal way. So everyone can cheer now. So we're not going to do these proofs formally, but we're just trying to get the idea across. Because trying to manage like 5 different numbers of like 0s, 1s, and 2s, that could be a giant pain in the you-know-what, okay? So let's actually prove a result here, unless there are questions about the lemma itself. Woohoo. Someone fixed it. Okay, cool. So let's actually prove a language is not context-free. Let's do the example that I mentioned last time, which is this one. So some number of 0s, then the same number of 1s, same number of 2s. And I claim that it's not a CFL. So we'll definitely prove it's not a CFL. Don't worry about that. But what was our intuition for why it isn't a CFL? What made it difficult? Yeah, the 2s. Because our idea for the PDA was to put the 0s on the stack as we're reading them. Then we pop off the 0s with the 1s in tandem, so everything's okay there. But when I get to the 2s, the stack is empty now. So I really don't have any knowledge of how many 0s there were. So there's nothing I can really do there. Okay, so, but remember, is that a proof that it's not a CFL? That I can't think of a way to do it, therefore there's no way to do it? No. So just be careful of that. So let's prove that this is not a CFL. So proof. So how do we begin? Let's jog our memories for how we start these.
Yes.
Yeah, assume that it is a CFL. And thankfully, proofs like these will go through and have the same structure as the regular ones, so we kind of have some intuition of how to approach these, so it's not as big of a leap as before. Okay, great. So assume that it is a CFL. Then what do we do then? Yeah, there exists a P for L. So again, I'm going to shorthand it because we know what it means. There exists that constant P for L. Great. And then what do we do?
String.
Yeah, we pick a string with what two properties? In the language and a length at least P. So remember, you know why I'm like emphasizing that, right? Because most students miss that on the midterm, okay? So will I see such a big problem with that on the second midterm? If a question like this appears. No, so remember, in the language, it must be in the language and long enough. If it doesn't satisfy both of those, we can't say anything. If it does, then we can, possibly. So let's choose a string. Any suggestion? What is a really easy one? Yeah, P for all of them. So whenever you see n in the exponent, that usually indicates put the P in the exponent where the n is. That's not always true, but usually it's the good idea. So 0 to the P, 1 to the P, 2 to the P. It's in the language because it has the right structure. And it's very easily shown to be long enough. It has 3 P characters. Cool. Oh, by the way, is this language regular? No, in fact, for the same thing. If we pump in the zeros, put more zeros in, for example, then it will have a different number of zeros than ones and twos. Ignore that proof for now, that we can just pump in the zeros to get out of the language. What if I just prove this directly and ignore the regular result? If we prove this, that it's not a CFL, what does that prove about whether it's regular or not? Yeah, it can't be regular. Why is that true?
If it's not a CFL, that means
It's not regular. What's the contrapositive of that statement? If it is regular, then it is a CFL. Is that true? Yeah, because every regular grammar is a context-free grammar already. Or, equivalently, every DFA is already a PDA, that just doesn't use its stack. So, if we prove this, then it'll immediately show that it's not regular, which is kind of nice. So, okay, great. So, do we need to look at just one decomposition to show that it's not a CFL, or all decompositions? Yeah, all decompositions. Cool. So let's see what happens. We're not going to approach this in a formal way. You can, but it's just a lot of work, and it's just not worth our time. And it doesn't tell us anything interesting. So let's look at the 3 conditions again. In particular, the third one. It says that the middle 3 pieces where the 2 repeating parts are, the V and the Y, that it has length at most P. That's what the third condition says. Well, let's look at our string again. Well, could it be that those 3 parts are entirely in the zeros? Yeah, there's no specification on the first and the 5th part, the U and the Z here. Only the middle 3 pieces have the length requirement. So it could be that those 3 are entirely in the zeros, or they're entirely in the ones. Is that possible? Yeah, there's, again, no specification on U or Z. Could it be entirely in the 2s? So now let's look at a little bit more interesting situation. Could it be that the VXY part, so here's a technical term, straddles the midpoint between the zeros and the ones? And what I mean by that is the VXY part contains some zeros and some ones. Could it be there instead of just uniformly in the zeros, ones, or 2s? I'll draw it to make it a little easier to see instead of just me hand waving it. Okay, so here's our string. So we established that it could be entirely in the zeros, it could be entirely in the ones, it could be entirely in the 2s. Right, so those are the 3 obvious cases. Could it be that some of the zeros are in it and some of the ones are in it also? Yeah, it could be, because you can think of this like a sliding window. It could be of of length at most p, just a sliding window across the entire string. Oh, for that reason, could it be some of the 1s are in there and some of the 2s are in there? Yeah, that could be. Now, think carefully about this last situation. Could it be that it contains some 0s, some 1s, and some 2s? No, why not? Right. It has length at most p. But if it had some 0s and some 2s, then it must have length at least p plus 2. Because it must span the entire set of 1s, which has p of them, and at least one of the other 2. So that's clearly violated. So think about that last situation obviously can't occur for that reason, because it violates the length requirement. So let's look at the other 5 cases. So could it be that I pump into any one of those 5 scenarios? I put more of something in the string, and the number of 0s, 1s, and 2s goes up or down uniformly the same? Well, consider what happens. If it's just in the 0s and I put more 0s in, obviously the number of 1s and 2s are going to be the same, different than the number of 0s. Is that in the language anymore? No, so that leaves. And for the same reason, if we did it in the 1s or in the 2s, it would give the same result. What if we pumped in the 0s and the 1s? So the 4th case here, where we have some 0s, some 1s. Well, the number of 0s and 1s is obviously going to go up, but the number of 2s doesn't. So it leaves the language. And same scenario for the 1s and the 2s. Because if I put more of 1s and 2s in, the number of 0s stays exactly the same, and therefore we leave. Cool. So that's actually it. So if we pump up any amount, say I equals 2, for example, for any decomposition, it is impossible for the number of 0s, 1s, and 2s to increase the same amount. And the proof for why that's true is the reasoning that we just gave. If it's just in one of the 3 parts, then we're out of the language, because the other 2 sets of those symbols don't change numbers, only the 1 does. And if we pump in just 2 of them, then the 3rd one is left unattended. And the case of if we want to pump in all 3, that's impossible due to the length requirement. And so no matter what happens, if we have any one of those 5 scenarios, no matter what, we leave the language. So for any decomposition at all, we leave the language no matter what happens. So what does that tell us? That no matter what we do, we leave the language, therefore the language is not a CFL. So for that reasoning, L is not a CFL. Okay? Does that make sense? At least a little bit. What about, so we're not going to do another one. This next one we're not going to do in full depth, but we'll do another one after that. Well, consider instead of this language, let's consider this other one, and I'm going to put it in red. So I'm going to call it L prime, and it's almost the same, but it's not quite the same. So it's all strings that have 0s, 1s, and 2s in them, but the number of 0s, 1s, and 2s is the same in W. Okay? So it's not this. Why is it not the same language? Yeah, the order doesn't matter. So the first one, it has to be zeros first, but here it could be any order. Based on our proof already of the 0n, 1n, 2n, 1, what do we know about L prime? Could we use exactly the same proof? Well, let's see. Well, maybe not exactly, L prime instead of L, but assume that the L prime language is a CFL. Is the string that we picked here good for L prime? Yeah, it's in the language, same number, just has a specific order, and length at least p, that's fine. Well, no matter what happened, we got a different number of zeros, ones, and twos. So no matter what happens here, because we got a different number of the three sets of characters, we leave L prime also. So what can we conclude about L prime also? It's not a CFL either. So for the exact same proof, L prime is not a CFL either. That's pretty interesting, that we can use the same proof here. Any questions about that? And for obvious reasons, because L prime is not a CFL, it's not regular either, for the same reason. Any questions about the proof itself? So we're not going to actually prove this next one. I just want to mention it to you. So what was one of the other examples that we did when we did the regular Pumping Lemma version? The two harder examples, quote unquote. The primes and the perfect squares one. So if you do the exact same proof there, it turns out that these two languages, I'm going to call them L1 and L2. So these are the languages we talked about before. These are not CFLs either, for the exact same proof. And why can we conclude that it's the exact same proof? So I'm going to actually state a result, and I'm going to sketch why it's true. So if a language L is unary, so, and by this I mean that it's a subset of, say, 0 star. The only meaning behind unary is that it has only one character. There's not two characters. If it's unary, then L is regular if and only if L is a CFL. Yeah, go ahead. So it's going back to the proofs that we did before, and I'll sketch why it's true. What's that?
Like we didn't do those proofs today. Like the proofs that we did like a week or two ago.
Yeah, they're the same proofs essentially. Yeah, yeah. Because we're gonna be and I'll sketch why that's true. But yeah, so here's actually a really interesting result, which is if you have a unary language, then if you show it's not regular, it's not context-free either, and vice versa. So this is actually really interesting because this tells us right here that your compiler, if you wrote a program that checks if a number is prime written in unary, there's no way for that compiler to check if that program's correct at all. Because if it could, then this language would be context-free, but it isn't. Because most compilers are implemented using a context-free grammar, essentially. So why is this true? So I'm just going to sketch it. And I don't expect you to know this. I'm not going to test you on it at all. But it's just interesting to note. So why is this true? So consider if this language is unary. There's only one character. We'll go back up to the statement of the pumping lemma here. So it says that if we have a unary language, then if it's a CFL, then it's also regular. So we know that if a language is regular, it already is a CFL. So we only need to show that if we have a unary context-free language, it's also regular. So let's look at the pumping lemma statement. So if you look at this, we're really pumping the V and the Y part. But because the language is unary, we're really just pumping the same character. So does it really matter where I pump in the string? If we have a unary language with just a single character, a bunch of zeros, does it matter if I pump in the middle or the end? Or the beginning? It doesn't matter at all. So in fact, we might as well just pump at the beginning. But the pump part I'm pumping has length at most p characters, which sounds suspiciously like the regular version. And in fact, that's the case. So that's just a high-level argument for why this is actually true. So based on that, these two languages are not context-free. Okay, any questions about that? Okay, so let's do one more, and let me try to think of an example because I don't know one right now. Let's see. Yeah, I'll try to think of an example. So let's do this one. So let's call it L3, and I'm making it up on the spot, I promise. Let's do, okay, yeah, let's do this one. So let's do, it's very similar. So 0 to the p, yeah, not p, n plus 2, 1 to the, actually no, let's make it a little bit more interesting than this, sorry. Let's make it 0 to the I, 1 to the j, 2 to the k, now I remember this. So then here we have that I is at least as big as j, which is at least as big as k. So this is not the same thing as n in the exponent. Here we could have more zeros than ones. I can't have fewer zeros than ones, obviously, but I have to have at least as many. So this is actually where it gets a little bit interesting. So let's actually try to prove that this is not a CFL. So let's just start as before by assuming that L3 is a CFL. Then there exists a P for L3, as you might expect. And then now we gotta pick our string, or a reasonable string here. So any suggestions? Yeah, so let's try this one. So I think you said P, then P plus 1, then P plus 2 or something? Or what did you pick?
Yeah.
Okay.
Can you choose them all as P and?
We'll get to that. So I think you picked this one. Or something similar. Yeah. I'm picking this string on purpose because it actually won't work. And we'll see why. So, but let's actually make our check. Go ahead.
It's not in the language.
Oh, sorry. You're right. Well, yeah. So why would I not pick this string? It's not in the language. Okay, good. Yeah. I hammered on pick a string in the language, and then I goofed up myself. The reason why I picked it was in CSE355, I remember it's not greater than or equal, it's less than or equal, so it would work then. But let's do the one I think was suggested, which was P plus 2 first, then P plus 1, then 2 to the P. I think that's what you picked. Okay. So now is this one in the language? Yeah. And it has length at least p, so no problem. Does satisfying those two requirements guarantee to me that a proof will work? No, not necessarily. And in fact, this string won't work. Why won't it work? Suppose that the VXY part was only in, let's say, the zeros. If I put more zeros in, is that going to help me get out of the language? No. So what is my only choice? Well, I can't put more in, so what do I do instead? I go back to I equals 0. I take out a copy of V and Y simultaneously. Okay? Well, how many zeros will I remove then, at least? Can I remove no zeros at all? If I take, no, I must remove at least 1 0. But could it be exactly 1 0 removed? Yeah. So one decomposition could be where V is empty and Y is a single 0. So if I try to pump out, then that's not going to get me out of the language. Yeah, so then for all I at least 0, I remain in the language. Remember, we got to show one value of I doesn't work. So, and for the same reason, if I have the V and the Y part both in the ones, for example, then I could have V be empty, Y be a single 1, and no matter which value of I pick, the number of ones is going to be at least the number of 2s. It's going to fail if I pump more for the number of zeros, but it's going to satisfy the other requirement for J at least K. So this string won't work either. What is a string that will work, do you think? Andrew? Yeah. So why will having the same exponent here be better? So I think I may have mentioned this, but in the case that I haven't, one way to approach these, or really any proof in this class, is pick a string that is right on what I call the borderline. So the absolute closest it could possibly be before, if we pump even a little bit, it'll go out of the language. So if we look at the string before, right here, we could remove 1 0 and it'll still stay in the language. But for the second string down here, if I remove 1 0, I'm immediately out of the language. Okay? So my advice is to pick a string right on the borderline so that pumping out becomes a lot easier. So this one's right on the borderline. It doesn't guarantee it'll work, but let's actually try it.
Can you only pick that because it's greater than or equal to?
Yeah, if it's greater than or equal to. If I instead said I strictly bigger than J, strictly bigger than K, then the example given would be the correct one because it's on the borderline in that case. So different strings for different scenarios, as long as you pick one right on the borderline for the one that you're given. Okay, so let's actually do this one. Well, what happens here? So if we're only in the zeros, what do? So we'll actually have to write cases out. So V and Y both in zeros. Well, what could I do? If I put in more zeros into the string, is that going to help me here? No, because the at least then condition is still going to be satisfied. What can I do instead? Yeah, take a copy of V and Y out. Yeah, so I'm not going to write everything out because it should be pretty clear why we're doing pumping down in this particular case. Because if we're removing a 1 0 at least, then we have a fewer number of zeros than ones, for example, and therefore we leave the language. Okay, great. What if V and Y are both in the ones? Which it could be in this case. I can pump down or up in this case. If I pumped up the jam obviously, then I would have more ones than zeros, which leaves the language immediately. So pump in this particular case in either direction. So I equals 0 works, I at least 2 also works. So any value of I other than 1, of course, will work here. Well, one of the other possibilities is that V and Y are both in the 2's. Which direction must we pump in this case? We must pump up. If I pump down, is that going to help me get more 2's than 1's, for example? No. So in this particular case, we have to pump up to say I equals 2. It doesn't have to be I equals 2, but anything at least 2 will be fine. Okay, great. Those are the 3 possibilities of what V and Y could be, obviously. Or are there other cases? What are the other cases? Yeah, so V and Y could have some zeros and some ones. It's not just in the zeros or just in the ones. So let's say that VY has zeros and ones. Ooh, what do we do then? Well, let's see. If we pump down, well, in this particular case, the number of zeros, of course, and the number of ones is both going to go down. So I may still be okay with the I at least J condition. I can still be in the language for that. But will I fail the J at least K condition? The number of, yeah, because the number of 2 stays exactly the same. So in this case, we'll pump, down to I equals 0. And the other case for the same reason is VY has 1s and 2s. And what could you expect we're going to do in this case? Yeah, pump up. Because if I pump down, I could still be okay with the J at least K condition still in the language there. But if I pump down, I still am satisfying the other one. So I stay in the language possibly. But if I pump up, then I am not anymore. So pump up to, again, say I equals 2. But any value at least 2 is fine in this case. Oh, then there's a 6th case that VY has zeros and 2s. Ooh, it's not possible. Why?
That's going to be longer than 1.
Ah, for the string we happen to pick, we leave the language. Oh, sorry, we don't leave the language. We can't go across the P set of 1s to get the zeros and 2s. So this case is not even possible. Oh, well, that's every single possible case. Oh, and in all 5 cases, what happened? Fail, and more concretely, that means? About the string that we generated. Is it in the language that we generated? No. So for that reason, L3, I think, L3 is not a CFL. Isn't this a lot easier than managing U equals 0 to the alpha, V is equal to 0 to the beta, 1 to the gamma? Isn't this a lot easier? I think for me, it's a lot easier at least. Maybe for you it isn't, but to me it is. But any questions about it? Oh, what about the language, not necessarily of this form, but any string of zeros, ones, and 2s, where the number of zeros is at least the number of 1s, which is at least the number of 2s. So just like before when I just say they can be in any order, what about that language instead of just this one? It's not context-free either, because the string we picked is also in that language too, and the 5 conditions, the 5 possibilities, we ended up with a different number of 0s, 1s, and 2s every single time. So we didn't rely on the order of the 0s must occur first, or the number of 1s must occur second. So in fact, for this reason, if we look at the language zeros, ones, and twos, where number of zeros is at least the number of ones, which is at least the number of twos, I guess in W, is also not a CFL. Pretty cool. So in fact, even really simple languages are not CFLs. Even with this additional power, they're not context-free. Okay? Any questions about these proofs in general? Because it might be time to take a break. I know I need one. Okay, let's take a break.